Hello, welcome to Control Systems Lectures. In our previous lectures, we've been dealing with single subsystems represented with a block with an input and an output. However, most control systems are made up of several subsystems interconnected. Since it is easy to calculate the response of a single transfer function, it is therefore our desire to reduce the multiple subsystems to a single transfer function. This will then allow us to use the techniques of the previous lectures to obtain transient response information of the whole system. Therefore, at the end of this lecture, you will be able to do the following. 1. Reduce a block diagram of multiple subsystems to a single block representing the transfer function from input to output. 2. Convert block diagrams to signal flow diagrams. And 3. Find the transfer function of multiple subsystems using Mason's rule. Note that these lectures are based on your textbook Control Systems Engineering Chapter 5, the 6th edition by Norman Nice. A subsystem is represented as a block with an input, an output, and a transfer function. When we have several subsystems interconnected, some elements will have to be added. These are the summing junctions and the pick-off points. The arrowhead indicates the direction of the flow of the signal. Summing points will always indicate if the signal entering the junction is positive or negative, and the signal out of the junction is the algebraic sum of all the signals into the junction. The pick-off junction, as shown in this diagram, distribute the input signal out of S. We will now introduce different topologies of control systems models. The first form is the cascaded subsystems as illustrated in this diagram. You can see that the intermediate signal values are the output of each subsystem as shown here. Therefore, the subsystems can be reduced to an equivalent block diagram as shown in figure B. And the equivalent transfer function G subscript E defined as the output Laplace transform divided by the input Laplace transform given by equation 1. This next figure shows an example of a parallel form. We can arrive at the equivalent system by writing the output of each subsystem to reduce the system to figure B. The equivalent transfer function is then given by equation 2. Now we come to the feedback form, which is a very important topology for dealing with complex subsystems. The feedback system forms the basis for our study of control systems engineering. In the first lecture, we defined the open loop and the closed loop system, which is also the feedback system. We also gave the advantages of the closed loop over the open loop systems. Our focus going further in this class will be on the closed loop systems, which is shown in figure A. In this simplified model, we can write the equation for the error signal as E of S is equal to R of S minus or plus C of S H of S. Let us call this equation 3. But we know that C of S is equal to E of S multiplied by G of S from the figure, from which we can then write E of S is equal to C of S over G of S. Let this be equation 4. Substituting equation 4 into 3 will give us equation 5, which is C of S over G of S is equal to R of S minus or plus C of S H of S. Simplifying equation 5 will yield C of S over R of S, which is equals to G of S over 1 plus or minus G of S H of S, where C of S over R of S is the equivalent transfer function for the feedback model. Also note that the product G of S H of S is called the open loop transfer function or the loop gain. So far, we have covered the three main topologies or forms in block diagrams. These are cascaded, parallel, and the feedback form. These three forms are usually combined into complex arrangements in physical systems. Therefore, recognizing these topologies in the complex arrangement is a prerequisite to obtaining the transfer function of a complex system. Our goal is to reduce complex systems with multiple subsystems into a single transfer function. It is not always apparent that the familiar forms are recognized immediately from a block diagram. Therefore, we will have to know how to create familiar forms from a complex system. These figures show the equivalent diagrams when transfer functions are moved left or right past a summing point. This next figure shows the equivalent block diagrams that are formed when transfer functions are moved left or right past a pickoff point. Let us demonstrate all we have learned in an example. In this example, we are to reduce this block diagram to a single transfer function. We can see immediately that we can collapse the three summing points into a single one, yielding the next figure. Next, note that the three feedback functions, h subscript 1 of s, h subscript 2 of s, and h subscript 3 of s, are connected in parallel and are fed from the same signal source, and their output are summed to give an equivalent function, which will be h subscript 1 of s minus h subscript 2 of s plus h subscript 3 of s. Also recognize that g subscript 2 of s and g subscript 3 of s are cascaded. Taking these together further simplify the block diagram to this feedback block form. And finally, the feedback system is reduced and multiplied by g subscript 1 of s to give the equivalent transfer function given by this last figure and its equation. Let us demonstrate how these concepts can be used for analysis and design of control systems. Recall that our goal in reducing the complex block diagram to a simple feedback form is to be able to analyze and/or design the controller. Therefore, let us say from a complex system we arrived at this feedback system, which could represent any physical system. We can compute the system's transfer function using the equation T of S is equals to G of S over 1 plus G of S H of S, which we developed previously. In this case, our G of S is equals to K over S into S plus A, and our H of S is 1, which is a unity feedback. Substituting these into equation 1 and simplifying will yield T of S is equals to K over S squared plus AS plus K. Please verify this for yourself. Note that as K varies, the poles, that is the roots of the characteristic equation, will change, and you can have either an overdamped, a critically damped, or an underdamped system. For example, for K between 0 and A squared over 4, the poles of the system are real and located at S1 of 2, that is the 2 poles, equals to minus A over 2 plus or minus square root A squared minus 4K over 2. As K increases, the poles move along the real axis and stays overdamped until K is equals to A squared over 4, when the poles then become repeated and the system becomes critically damped. For gains above a square over 4, that is for k above a square over 4, the system is underdamped with complex conjugate poles located at S12 equals to minus a over 2 plus or minus j square root 4k minus a square all over 2. With this set of poles, we can see that as k increases, the real part remains the same while the imaginary part increases. In this situation, therefore, the peak time decreases and the percentage overshoot increases while the settling time remains constant. It is these characteristics that enables the engineer to analyze and/or design the controller. Let us demonstrate this with some examples. This is example 5.3 in your textbook, and you'll find this in page 246 if you're using the 6th edition. And the question is to find the peak time, the percentage overshoot, and the settling time. So in order to do this, we first need to find the transfer function of the system. So that's the first step. And this is going to be using the equation T of S, which is G of S over, since we have a unity feedback, it will be 1 plus G of S H of S. Now this is a unity feedback control system. Once there is nothing on the feedback loop, then it's a unity feedback, which means that our H is equals to 1. So and our G of S will be this whole quantity. So this is G of S. If we now substitute this into the equation, we will have our T of S will be equals to 25 over S plus 5 over 1 plus 25 over S plus 5, multiply of course by 1, and this should give you 25 over S squared plus 5S plus 25. Always verify this. When I jump steps, you need to verify for yourself. So our characteristic equation will be S squared plus 5S plus 25 is equals to 0. So the first thing we want to do is to find omega n and our zeta. So from the characteristic equation, we know that omega n squared is equals to 25 from our generalized second order equation. And so from here we know that omega n is equals to 5. And then we also know that 2 zeta omega n is equals to 5. And from here we can find zeta to be equals to 5 over 2 times 5, and this will give us 0.5. So this is our zeta, and this is our omega n natural frequency. And from here is smooth sailing. The peak time is given by the equation pi over omega n square root of 1 minus zeta square. And if you substitute the values, this will be pi over 5, 1 minus 0.5 square, all things square root, and this will give us 0.726 seconds. And then our percentage overshoot is equals to e raised to the power minus zeta pi over square root. Okay, so we have omega over omega n square root 1 minus zeta square, and all of this multiplied by 100. So if you substitute for your zeta and for your omega n, you will then arrive at a percentage overshoot of 16.3%. And then our settling time for this system is given as 4 over zeta omega n. So this will give us 4 over 0.5 times 5. This will give us 1.6 seconds. So this is how to use the reduced form or the feedback system to arrive at the transient response characteristic of the system. Now we're going to look at an example that involves the design. So this question says that you should design the value of the gain K, and this is our K, you can see is the gain for the feedback control system of this figure, so that the system will respond with 10% overshoot. So our desire is to have a percentage overshoot equals to 10%. That's the goal. So again, we start by finding the transfer function of the system, and I'm not going to write the equation, I'm just going to write the transfer function. It's going to be K over S square plus 5S plus K. You can see that the characteristic equation is dependent on the value of K, and that's why it's a design parameter. As we change K, we can change the percentage overshoot. So we now have that. Next, we find omega n, the natural frequency. So omega n squared we know will be equals to K. So K. So from here, we can see that omega n is equals to the square root of K. Then we look for zeta. Then 2 zeta omega n is equals to 5. And so from here, we can also see that our zeta is then equals to 5 over 2 square root of K. Now recall that the equation for the percentage overshoot is equals to E raised to the power minus zeta pi over square root of 1 minus zeta square. Multiply this whole thing by 100. So you can see that our percentage overshoot is dependent on zeta only. So we equate the equation for the percentage overshoot to equals to 10 because that is our desired percentage overshoot. Or we can have e raised to the power minus zeta pi over 1 over square root of 1 minus zeta square equals to 0.1. So we can then say that minus zeta pi over square root 1 minus zeta square is equals to natural log 0.1. And from here we can then compute for our zeta. You will be able to find from here, you can finish up the analysis from this point and you arrive at zeta will be equals to 0.591. So now we know what our zeta is, but the question is to find the k value. So we go back to our equation for the zeta. We said that zeta here, we said it is equals to 5 over 2 square root k. So we will then write 0.591 is equals to 5 over 2 square root of k. So from here, this is 9. From here, you can find your k value to be equals to 17.89. So this is how we've used this to design the system by finding the k value that will give us our desired percentage overshoot. In summary, we have introduced the block diagram algebra method. 3 topologies or forms of block diagram arrangement were introduced. These are the cascaded, parallel, and feedback arrangements. We further showed how to simplify complex block diagrams to a single transfer function form. The concepts taught were used to demonstrate how to use them for analysis and design of control systems. Some examples were then presented, and that's what we've covered. In the next lecture, we will be looking at the signal flow method and the Mason's rule. Hello, welcome to Control Systems Lectures. In this lecture, we will consider the signal flow graphs method, which is an alternative to the block diagram method. In this method, the signal graph, it makes use of branches which represent systems and nodes which represent signals. These are shown in this figure. A system is represented by a line with an arrow showing the direction in which the signal flows. Adjacent to the line, we write the transfer function, like G1 of S, G2 of S, and so on and so forth. A signal is a node with the signal's name written adjacent to the node. Figure C shows the interconnection of the systems and the signals. Each signal is a sum of the signal flowing into it. For example, the signal V of S is equals to R1 of S, G1 of S, minus R2 of S, G2 of S, plus R3 of S, G3 of S. And then the signal C of S, or C subscript 2 of S, is equals to V of S, G subscript 5 of S. And here you can then substitute your V of S. And then we can also see that the signal C subscript 3 of S is minus V of S, G subscript 6 of S. And here again, you can substitute your V of S. In order to show how the signal flow diagrams compare with block diagrams, we will convert the cascaded, parallel, and feedback block diagrams to signal flow diagrams. Let us start with the cascaded form, which is reproduced here. The first step is to draw the signal nodes for the system. And then secondly, we interconnect the signal nodes with the system branches. Next, let us consider the parallel form. We use the same procedure as before. Draw the signal nodes and then interconnect the signal nodes with the system branches. The same procedure is carried out for the feedback form. However, take note of how the arrow of the feedback loop, which has to go in the opposite direction to the feed-forward elements. Let us consider an example, the example 5.6 in your textbook. We are to convert this block diagram to a signal flow graph. Step 1 is to draw the signal nodes. Secondly, interconnect the nodes with the transfer functions showing the direction of signal flow. Note that the negative signs at the summing junctions of the block diagram are represented by the negative transfer functions of the signal flow graph. Finally, we can further reduce the diagram by eliminating signals that have a single flow in and a single flow out. These are V subscript 2 of S, V subscript 6 of S, V subscript 7 of S, and V subscript 8 of S. This will lead to this last simplified signal flow graph. Now that we know how to develop the signal flow graphs, let us show how to reduce the signal flow graphs to a single transfer function, just as we did using the block diagrams algebra method. The signal flow graphs method requires the use of a formula, which was derived by S.J. Mason when he related the signal flow graph to the simultaneous equations that can be written from the graph. Generally, this method is prone to making mistakes, and hence a lot of care should be taken in applying it. Most mistakes are as a result of the presence of non-touching loops. We will come to that later. However, when a system does not have a non-touching loops, it is easier to apply the signal flow method than the block diagrams. The Mason's formula has several components and we need to define them. We will use this figure to define and explain the components in the Mason's rule. The first component is the loop gain. This is the product of branch gains of a loop that starts at a node and ends at the same node without passing through any node twice. In this example, there are 4 loop gains. The first one is G subscript 2 of S, H subscript 1 of S. The second one is G subscript 4 of S, H subscript 2 of S. The third is the G subscript 4 of S, G subscript 5 of S, and H subscript 3 of S. And the last one is G subscript 4 of S, G subscript 6 of S, and H subscript 3 of S. The next component in the formula is the forward path gain. This is the product of gains along the path from the input node to the output node in the forward direction of signal flow. And for this example, we have 2 of them. These are the G subscript 1 of S, G subscript 2 of S, G subscript 3 of S, G subscript 4 of S, G subscript 5 of S, and G subscript 7 of S. And the second one is G subscript 1 of S, G subscript 2 of S, G subscript 3 of S, G subscript 4 of S, G subscript 6 of S, and G subscript 7 of S. The next element is the non-touching loops. These are loops that do not have any node in common. In this example, loop G subscript 2 of S, H subscript 1 of S does not touch loops G subscript 4 of S, H subscript 2 of S, G subscript 4 of S, G subscript 5 of S, H subscript 3 of S, and G subscript 4 of S, G subscript 6 of S, H subscript 3 of S. And finally, we have the non-touching loop gains. These are the product of loop gains from non-touching loops taking 2, 3, 4 or more at a time. In this example, we have 3 of them. So we have the product G subscript 2 of S, H subscript 1 of S, multiplied by G subscript 4 of S, H subscript 2 of S. Second one is G subscript 2 of S, H subscript 1 of S, multiplied by G subscript 4 of S, G subscript 5 of S, H subscript 3 of S. The third one is the product of G subscript 2 of S, H subscript 1 of S, multiplied by the G subscript 4 of S, G subscript 6 of S, and H subscript 3 of S. We are now ready to state the Mason's rule. It states that the transfer function C of S over R of S of a system represented by a signal flow graph is given by this equation, where K is the number of forward paths, T subscript K the kth forward path gain, delta is equals to 1 minus the sum of loop gains plus sum of non-touching loop gains taken 2 at a time minus sum of non-touching loop gains taken 3 at a time minus sum of non-touching loop gains taken 4 at a time, and it goes on and on. And then our delta subscript K is equals to delta minus sum of loop gain terms in delta that touch the kth forward path. In other words, delta subscript K is formed by eliminating those loop gains that touch the kth forward path from delta. In this class, we will use the block diagram algebra mainly. However, if you want to get a better understanding and a feel of the Mason's rule method, I will encourage you to go through the work example in page 252 of your textbook. In the next lecture, we will start with the topic of stability. Thank you for watching.